deep neural network can be used not only for supervised learning but also for unsupervised learning. So in this video, I'm going to describe how we're going to use a deep neural network for dimension reduction. And in particular, we're going to talk about the variational autoencoder algorithm. First, let's talk about what is autoencoder, and you can view it as just a fancy name for dimension reduction or data compression. Our original data is d-dimensional, and we want it to reduce to a k-dimensional vector. Once we get some jargon, once we get x, d-dimensional want to compress to a k-dimensional code or vector. That's called the encode. It's the encoding part. And once we receive that z, we want it to go back to the original x space. That's called the decoding part. If we restrict both the encoder and decoder are linear functions, that means our z is equal to some matrix times x, and given z, and we can get back to the x space by multiplying some matrix. And naturally, we wanted to minimize the loss or difference between the input and the output. So we can use this mean square error, and we sum over all the data, and we, of course, it is natural to find those two matrices to make sure this loss is the smallest. And you're going to find out that's essentially going to give us the PCA algorithm. Of course, now with deep neural network, we do not have to focus only on linear transformations. So both the encoders and decoders can be nonlinear functions. Now, in order to talk about variational autoencoder, I wanted to stick to this kind of a PCA framework. First, I wanted to describe what is a probabilistic PCA. For introduction, kind of a review or more detail on this topic, you can check those papers, especially in I think chapter 12 from the pattern recognition and machine learning book will be a very nice review on this topic. So what is a probabilistic PCA? We're going to assume, we're first going to think about a data and a generative model to describe this dimension reduction under the linear setting. So we're going to assume our k-dimensional latent vector zi is generated from a Gaussian distribution with mean zero and a standard and covariance matrix. And given zi and some parameters, we can generate our d-dimensional vector x. So what is the this mechanism? We can assume underlying a Gaussian kind of a linear model setup. My xi is equal to the latent vector times a matrix. So w must be d times d by k, and then that's a mean vector, and then plus some Gaussian random error over the d dimension with variance sigma square. With this setup, we could just solve the MLE of the parameter. Here by parameter theta, it basically contains these two parameters, w and the matrix w and the sigma square. We could obtain the MLE estimate of this w and sigma square directly. This is just because we have this z follow this model, and x given z and theta follow another model, and we can integrate over z, and you're going to find out because the mean of z is 0. So once we integrate over, the mean for the new xi will still be 0, but the variance is going to be different. So we have w transpose plus sigma square times identity. I'm going to go to the next slide, where we're actually going to use our EM algorithm to solve w and sigma square, which seems like useless because we are able to find MLE directly. This is just a Gaussian model. I'm going to come back to explain why what is the potential advantage of doing an EM algorithm. So first let's describe the EM algorithm. And here's our model, latent variable, and given latent variable and the parameter, this is sort of a nice Gaussian distribution. And so in EM algorithm, if you remember the EM algorithm, and when we describe mixture model, let's see. So the EM algorithm, okay. So this is the EM algorithm, and this is one particular slide. Now I just want you to, instead of thinking about the E step and M step, we described an alternative view of EM, which essentially just an MM algorithm, meaning maximization. In the following sense, we can come with a objective function which involves two parameters. One is the original parameter, another is a distribution over the latent variables. And we have an objective function like this, and then the EM algorithm basically try to maximize this by fixed theta value maximize Q, and then fixed Q maximize and theta, kind of iteratively. So let's get back to this probabilistic PCA. Here we just going to formulate our EM algorithm. The objective function, we have it is an objective function involving the parameter theta that will contains W and sigma square, and also the Q distribution over all those latent variables. I used to write the latent variable Z in uppercase, just try to remind you we're going to actually integrate over Z. But in this case, I think I have already used, because we're going to use uppercase for matrices, so I'm going to stick to this lowercase z. So this is a likelihood, and this is a prior, or the distribution for the latent variable zi, and the Q distribution is just some distribution over z. So in our EM algorithm, you're going to find out we're going to start with some initial guess of W and sigma square. And then we find out what is the optimal Q which can maximize this objective function. And you can look at the paper and references I listed here, or just take what I said as a given. You're going to find out the optimal Q can be factorized over each individual Zi. So the optimal Q will be the conditional distribution of Zi given the observed X and the current estimating of theta. And you're going to find out it actually follows a normal distribution. So we know the Q, and then given that Q, we're going to recalculate this objective function. Now treat it as a function of theta, and then we're going to optimize theta, and then you do that iteratively. Now let me go back to the previous slide and try to explain what is the potential advantage of using this EM algorithm instead of directly to maximize the likelihood. Now, if you wanted to maximize the likelihood, you work with this likelihood. Then, essentially, to estimate W and sigma square, you have to work with the covariance matrix of Xi, sample covariance matrix, and then essentially you're going to find out you have to deal with the inverse, and when you do all the calculation. Now that's the inverse of a D by D matrix. D is a dimension of X, which we assume is going to be large. But in the EM algorithm, and we also going to encounter the calculation where we have to invert the covariance matrix of a Gaussian distribution, which is here. But that's we're dealing with Gaussian distribution, Gaussian random variables in K dimension. K is the dimension of the latent vector Z. K is much smaller. The dimension of Z is much smaller than X. So that means here, in terms of computation, the EM algorithm is much more efficient because we only need to invert K by K matrices instead of a D by D matrices. So that's a potential advantage of using a EM algorithm to solve this probabilistic PCA. Okay. So how we're going to go from probabilistic PCA, which is a setup here, to variational autoencoder, we are going to go through the following 4 steps. First, I'm going to reformulate this and try to convince you we're going to use, instead of using EM algorithm, we're going to use variational EM algorithm. And then now we talk about what, how to do a amortized inference. So we're essentially going to do amortized variational inference. And then we're going to introduce deep neural network by replacing a lot of models by DNN. And then at the end, we have to use reparameterization trick, because the loss function we're going to deal with is not the ordinary loss function. So we have to use reparameterization trick, and so the derivative can be computed more efficiently. Okay, so let's go through those steps. First, this is an EM algorithm. Remember, this is an objective function where theta is the parameter, and the Q is basically any distribution over all the latent variable z's. As I mentioned, when you derive the EM algorithm, you're going to find out actually this distribution, the optimal choice for Q, it turns out you can factorize that over. So the optimal choice for Q is actually a factorization over those n latent variables. So the optimal choice is going to be some distribution over z1 times some distribution over z2 and go on. Now, as I mentioned, we're going to do some other transformation of this whole thing. So first I wanted to propose just to require, instead of looking for n in Q, I'm going to just focus only on factorized Q. So the Q distribution, the choice for Q over those n latent variables, and we just only look at the factorized version. Now you may ask, well, it seems like there's no change, because we already know the optimal choice is going to take this factorized form. But as I mentioned, you have to keep in mind later we're going to change other part, and then it is possible the optimal choice for Q is no longer take this factorized version, but we're going to just make this restriction. We only look at, and when we do the optimization, we only look at the factorized form, and the purpose is for efficient computation, tractable computation. So first we require the Q the Q has to be a factorized version over those individual zi's. And second, I even wanted to further require each of the distribution over zi going to I require them to be from a particular parametric family. For example, in this setting, I will require those Q distribution over zi must be normal with some mean and diagonal diagonal covariance structure. Again, we are making restrictions because that's just for our computation to be more efficient. And it is true by imposing those restrictions. So now you can see the objective function, I even changed that Q to be just a collection of those parameters, because we already know we're not looking at any Q. We only look at Q from some parametric families. So we just wanted to estimate those parameters. So it is true the optimal value for J, which can be obtained here, won't be the same as optimal J here in the original setting. So there must be some discrepancy, unless the truth is this is actually the truth, but usually this is not. So it is true that the optimal value here won't be the same as the original unconstrained optimal value, but that's a bias we are willing to have. So that's basically saying now we move from EM algorithm to variational EM algorithm, restricting the choice of Q, and that's basically the variational approach. Okay. So now we here in the variational, we already decided to change our only focus on Q, which and going to we have individual Q for each Zi, for each latent variable, and in particular, they are from some parametric family with parameter phi I. So here's an issue here. Now, for every data point xi, we're going to obtain a phi I. Of course, that phi I will depend on xi and some estimate of theta, but it's definitely a function of xi. But that dependence function is not that clear. We just sort of in our variational EM algorithm, for every data point we have some formula to update the phi I. So one approach is called the amortized inference, in the sense that, well, instead of calculating, inside this, in our variational algorithm, every time if you calculate that phi I in our algorithm, we're just going to learn a mapping. Meaning, if you give me xi, I'm just going to plug into the function. I know what is a parameter, which is approximation, but hopefully we can approximate it very well. So we're going to learn this mapping phi. What's important here is, originally we learn all those individual phi 1 through phi n. Now, if you give me a new data point x star, I actually don't know how to get the corresponding phi star. But in the new setting, what we learn is actually a function, which is a phi here, lowercase phi. That is, if you gave me a new x star, I plug into this learned mapping or function, and I know what is the parameters for the z star. The Q function for z star. So that's called amortized inference. Instead of calculating those individual parameters, we're just going to learn that mapping, approximate that mapping for phi. Okay, so far we have already changed our framework to variational inference and also amortized inference. So here's our model. Latent variable, given latent variable and parameter, we can generate our x. And then we're going to use variational EM algorithm to carry out a amortized inference in the following sense. We have an objective function where it is a function of the unknown parameter and a particular mapping phi. And we're going to pick j and phi to optimize. I think actually we wanted to maximize this. So this is not the loss function. We have to add a minus sign to get the loss function. We wanted to maximize this objective function, which is a product of this likelihood. You can think about the likelihood of x given latent variable and parameter, and this is the prior, or just the distribution for the latent variable, and the denominator is basically some distribution of zi given a parameter. We actually know the distribution family of Q. In this case, let's assume we already decided I'm just going to use a normal distribution. So the denominator is going to be a normal distribution over zi given a particular mean vector and a diagonal variance and matrix, where that mean and the diagonal variance is actually a function depends on xi, the input. Okay, so this is our objective function. And now we're going to have our third step. We're going to replace all the models by a deep neural network. So first, the pink model, which is given latent variable and some parameter, how can we get x? Well, that's basically the decoder part. So given z, we're going to get x. Now, instead of using any Gaussian distribution with a linear transformation, we actually going to let z go through some deep neural network and then get x. So here the parameter theta now becomes the parameters associated with this part, this segment of the deep neural network. Another model is, when we give xi, we're going to extract the mean and the variance of a Gaussian distribution in the k-dimensional space. That model or that mapping, we're going to replaced by a deep neural network, meaning given the x, how can we get the mean and variance for z? That part we're going to use a deep neural network to learn that mapping. So that's the encoder component. So far we have already changed that problem, the probabilistic variational probabilistic PCA setup to actually an autoencoder problem, right? You have the encode and decode. Now, but it is slightly different from the ordinary autoencoder, because the loss function here is not the same as the loss function. It's not like we measure the L2 difference between the input and output, right? So the loss function takes this seemingly complicated form. So let's take a look of the loss function. So for the loss function, we're going to just expand this. Well, because the Q is basically this distribution. So we are looking at this log ratio, but we're going to average out all the ZI. Here ZI, all the ZIs follow a normal distribution with mean and variance, which are determined by this phi mapping. So let's write this objective function in two terms. The first term is just expectation log of this term. So that becomes, log of a product becomes summation. So this part, this is the first component. And then the second component is basically expectation of the remaining ratio, this one divided by this, right? So I write it here. And so you're going to find out, I'm going to show you on the next slide, this one actually in closed form. Let's look at this first term. So the first term, the xi given so this is actually the log p, depending on how we're going to go from x to zi. So you can come with some kind of a loss function, and then there's a way you can just change to the give rise to the corresponding probability distribution. But there's a issue here is when we do deep learning, we have to take derivative. So we have the derivative over j, theta, and phi. We do have theta here, but the phi is actually hidden in the expectation part. So there is we would like to keep the expectation here, but we would like to make the expectation is independent of the parameter, because that will help us to simplify the calculation. Now that's what the last trick we have to use, called the reparameterization trick, because each of the zi is going to be normally distributed, and only randomness is just the error part. So we can reparameterize each zi to be the mean vector plus sigma I times the standard normal. So the expectation random is only in this part. So we can keep the expectation over those IID standard Gaussian distribution and sum over this part. So in practice, when we operate this, we can replace the expectation by Monte Carlo sample with one sample. So it's kind of a very extreme case. We're basically just going to generate one set of those epsilon 1 and epsilon n, and we can ignore the expectation, and then what we have is just this part, and that's just some kind of loss function, and we can plug into the deep neural network, and we can take derivative. Now let's look at this part, how those part depends on the parameter theta and phi. And you're going to find out this is just a standard normal, and the denominator is another normal with mean and variance, and then we have to take expectation of zi with respect to this Q distribution. So this is equal to, and we just do the calculation, and you're going to find out, well, we first have this half k log sigma squared term from the the offset ratio. And then we're going to, once we take log of exponential, we just get those, terms in the exponential component. And then we have to take expectation over zi. And you're going to find out the expectation over this part. And because you've done proper, there should be divided by 2 sigma squared here. So because you've done proper centering and normalization, so the expectation over this part is going to be a constant. So you just look at the expectation over this part. Now zi follow this normal distribution. So you can have a mean vector plus, the variance part. So this part you can add it back. So this term we computed, you can add it back to this loss function. So you will see this is an additional term appearing in those VAE deep neural network. For example, if you check the Keras page, and my code is, if not exactly same, it will be almost a copy of the code here. So you can see in their loss, VAE loss, you have the ordinary loss, which is from the log likelihood part I mentioned before. Then you have this additional term, which you're going to find out it's exactly the same as the term here with just a sign flip. This is just because what we are writing here is actually not the loss function, but minus the loss, because we wanted to maximize this. So you can look at the code I posted on Piazza. Also, you can find some interesting code, useful code online. The flow for VAE is very similar. You just set up your network. You have to define your new loss function, and you can just train your variational autoencoder. Now, what's interesting is after training, you can actually take only this segment of the neural network, and you just input some latent variables, and you can see what is the generated output look like. So that will be the fake images, for example, for the digits data. In my example, this is a code where we showed that if we the latent space is only 2-dimensional, so we can see how when we uniformly generate some latent feature in that 2-dimensional space, we can see what the image look like. Then that will help us to understand what exactly features the 2 dimensions, the 2 latent space, 2 latent directions are trying to capture.